Thank you very much for this introduction. Thank you for the opportunity to give this talk. As it was already mentioned, it's a common work together with my collaborators from FAU, Onono Adhikari and Wolfgang Tiki. Also, Roland Haas, who is present here in the audience, helped us a lot in conducting this project. So, initial data for compact binaries. Mostly, I'm going to talk about the binary neutron stars, and that's the plan of my presentation. I will start from the big picture of the physical setup, and that's the green part of my presentation. Then I will focus for a numerical part, and this is the main core of the presentation. And finally, I'll spend a couple of minutes to present the preliminary results. So let's start from the big picture. We are talking about binary neutron stars, and they are, in principle, far away from each other. So we cannot simulate the entire process from the very beginning. We need to start with the two binaries separated by some reasonable distance. And in this case, this reasonable distance, we decided to take as a 50 kilometers. And what we know about this kind of system is that the orbital period is roughly in order of magnitude of milliseconds. So on the other hand, we know that there is such thing like a millisecond pulsar in the from the astronomy. So it tells us that the orbital angular momentum is, at least in some cases, equally important as the individual spin. Another important phenomenon here is the orbit circularization. We know that even if we start from the highly eccentric orbit, due to the gravitational wave emission, there is such thing like the orbit circularization, and in the radius like we have here, 50 kilometers, mostly it's just almost circular orbit, which is very slowly shrinking, and during its parallel motion toward the center. So that's the big picture. So let's have a look at the mathematical side of this problem. Let's discuss the math which stands behind this kind of problem. To do this, we need a couple of assumptions. First of all, we need to assume that the orbital period in such a case is significantly lower than the entire process. And this picture over here can help us to build a mental picture of the situation which is happening actually. So it is the trajectory of the one star in such a diagram where we have a space and the time. So it allows us to see the tangent vector. This tangent vector actually is pointed toward the time, toward the future in the time, and it at different places of this trajectory, it points the circle. So we are able to construct the initial data for a circular orbit. It is also possible to construct it for an eccentric orbit, because actually we are interested in this very special point over here. We are talking about the initial data, so we don't have to follow by the entire orbit. We can work on the problem only here, and at this point, the ellipse is almost, it could be very easily actually obtained by some slight manipulation of on the original circle. So that's just a picture to describe the general idea. And the second equation tells us about the second approximation we need to do. We have this tangent vector psi over here, and it is separated into its part related to the time and the part related to the space. So this component points toward the future, and this component points to some spatial direction. So what we know about the tangent vector is, if we take the Lie derivative for most quantities, we can assume that this is approximately zero. For example, for a metric component, it's zero. For most of the hydrodynamic variables is almost zero. So that's a very good approximation in most cases, but unfortunately, it's not a good approximation for a tree velocity. And now let me explain why. Let's have a look at this picture. Let's assume that's the state of the neutron star at some moment. Now we have a spin. So we are talking about the case with a spin. So these green arrows point some direction in the space, and let's pick some point P, like over here. So after some time, we can assume that the star will be somewhere else. The spin supposed to be orientated in the same direction in the space. But if we follow by the tangent vector, if we follow by this killing vector psi, we end up with the point P over here. So initially, the point P was on the rotation axis, on the axis of the spin. So we shouldn't expect any velocity over there. In this case, it is far away from the rotation axis. So velocity supposed to be there, not equal to zero. And that's why this kind of assumption, it's not a very good one for a tree velocity. So it is possible to separate the tree velocity into two components. And the first part is the irrotational part. And in this case, we can apply this entire reason related to the Lie derivative of them with respect to the tangent vector. But there's another component which we need to deal in the other way. And actually, this is the way how we introduce the spin into this model. So so something to remember from this side is that the velocity is separated into two parts. The phi is a field of the velocity which we can deal using the Lie derivative of the killing vector, and there is some additional component related to the spin. So I'm very happy. I was very happy to hear the first talk today, because there was an introduction about the initial data construction. Now I'm not going to explain anything except to present that there is a set of equations. The first 6 of them are second-order elliptic equations to describe the fields, and the very last equation is the hydrodynamic equation, algebraic equation for an enthalpy. So in principle, we have fields and we have hydro. So these describe this space-time, and here we have the description of the hydrodynamic. So how to deal with this problem numerically? And now let me present the solving procedure. And again, I was very happy to hear the second talk because it was about this thin sandwich approach, and that's exactly what we have applied over here. So we need to start from some initial guess for a matter distribution. And the initial guess in this case is just to take 2 TOV stars in some distance and use it as a 0th step. So let's take this 2 TOV stars and ask general relativity what kind of fields fits to this kind of matter distribution. So in step 1, we would like to solve this set of equations using just a very artificially introduced matter distribution. This kind of matter distribution which we basically placed it, right? And since we have these fields, then we can ask this question again: what kind of matter distribution fits to this space-time convergence? So in fact, this is the very essence of the general relativity. The space-time tells the matter how to relocate, how to distribute over the space, and the matter tells the space-time how it's supposed to curve. So this is the very essence of the general relativity. And we need to do it iteratively because we start from the very artificial configuration and we expect the convergence after the reasonable steps of this iteration process. So we iterate the first and the second step as long as the previous step is almost the same as as the very recent one. So after we are satisfied, after this difference is lower than some a priori set error of tolerance, we can say, okay, that's the solution. That's the quasi-steady state of the matter, which describes our initial data, and we can apply them to some solver to proceed the time-depending simulation. So that's the general idea of constructing initial data. And now I would like to focus on the numerical code we are using. But maybe it's a good moment to ask about questions. Okay, we can back to the questions later. So let me.
There are questions.
I have a question. So, how much art is in deciding how to do these various iterations to solve the different equations one after the other? Is that something that one can automate, or is it something that you basically always have to do by hand and babysit the code?
You mean this tolerance error?
Yeah.
So some kind of information about the quality of the initial data it comes from the time-dependent simulations when we load the initial data, and then we can see some artificial peak. For example, looking at the Psi4. So the lowest this peak is, the better initial data are. So a priori, actually, I don't know if we have some kind of state-of-the-art idea how to do it, to say, okay, it is for sure a good result. But usually we know it takes like 5 days to produce the well quality initial data. So, but we don't have something like the limit which we must get, the minimal error. So, yeah, babysitting the code.
So if you're adding two stars into your initial test, how do you add spin?
Oh, the spin comes from this. The spin is an input. So the two TOV stars are just the density pressure distribution, and there's some additional. This is the input of the model. We can set the spin as a number and run the program with it. So it could be equal to 0. It could be not equal to 0. It's an input parameter of the model, and it is actually incorporated over here into all of these equations. Here we have phi. This is the velocity field, which we can deal well using this leader value of the killing vector. And then there's a spin. It's just a number. We added it by hand. Okay. So let's move on. So we need initial data generator, and in this case we are using code called sgrid. On the other hand, when we have initial data, we would like to go through the simulations. So we also need a solver for such simulations. Our initial data generator is the code, the numerical code called sgrid, and we are using Einstein Toolkit to make the simulations. So speaking about sgrid, it allows us to set the values of individual masses. It allows us to set the separation of the binaries and equation of state, individual spins, and eccentricity. On the other hand, we have Einstein Toolkit, and here we need to, that's exactly the moment when we need to talk about babysitting the code. Here we need to set a lot of different numerical details. We need to choose our output data, where we would like to extract gravitational waves. And in principle, babysitting this code is a time-consuming issue. So we have a sgrid which can generate initial data for us, and fortunately, Einstein Toolkit has a framework called Cactus, and Cactus allows us to write a turn. And this kind of turn is already written. It is called the DNS data reader, And this code, this term contains an extract from the S-grid, which can deal with the reading initial data and manipulating them. So just the power of the S-grid was compiled as a library and compiled together with our turn with the Einstein Toolkit Cactus code to make it possible to basically take our initial data, ask Cactus what exactly data are necessary to provide to start the simulations, and to start the simulation. So that's the basic idea. And I'm going to back to this slide later on, but before, let me say a few words about the S-grid itself. Let me give you some kind of flavor about the details of this initial data generator. So it is a numerical code written in pure C. It is parallelized and it's modular. In principle, it contains two modules. The one is, let's say, the core module, which is responsible for all hard work like solving differential equations, some Newton-Raphson procedures, some spectral decomposition, and so on. But there's another component, and in this case, this component is something we are using to generate a binary neutron star initial data. But this second component could be actually anything. You can incorporate any physical problem to this model instead of binary neutron stars. And actually, I'm going to discuss this kind of toy model in the next slides. So both parts, the main and the module, are steerable by the parameters. We need to impose some physical and some numerical parameters to make it work. So now over here, I have a toy model of S-grid, and we can basically assume we have some problem to solve. There are equations, non-linear elliptic equations to solve. I'm not going to talk about the physics of these equations because actually I have no idea what kind of physics they describe, but it is possible to implement them and to just track step by step what exactly is going on in S-grid to solve this kind of problem. So to do this, we need to determine when and which kind of functions should be called and when exactly. So what is necessary to provide to the S-grid is just this set of equations, and we need to linearize them and as well provide to the S-grid. And then we can just see how the entire procedure looks like. So there's the toy model, and I know it sounds like it's slightly separated from the main stream of this talk, but I will go back to this slide later on at the very end of my presentation. So then it became clear why I'm talking. So S-grid is a pseudospectral code. We operate on some fields. Let's assume this is the field U. In our binary neutron star initial data case, we had a conformal factor, we had lapse and shift. In this case, let's just think about this field as just a general field U. And what is necessary to do is to expand this field in some basis. Over here we have constant coefficients, and here we have some unknown a priori basis functions. So knowing this, we can also very easily deal with the derivatives, because these functions could be chosen, could be known analytically, so we can differentiate them, and the prescription for a derivative is very straightforward. There is the same coefficient and basically the function after the differentiation. So it will be in case of the spectral code. S-grid is a pseudo-spectral code because instead of the original values of the coefficients, we need them in the places where the S-grid has grid points. So we prefer to calculate the values of these coefficients at our grid points, but it's still not a big deal. We can just, it's a simple transformation region over here. It's just a simple matrix. We can go back and forth from one coefficient to another. So in case of this coefficient, also in case of the derivative. So it's not a big deal, but I just want to explain that it is necessary at this point. Very last comment over here. Here I just provided the description in a 1D case and as we did a 3D case. So there is just a 3D version of the same procedure. The expansion of the field using some coefficient and then basis functions. So now because I mentioned about the numerical grid, it is another important thing to underline that this kind of spectral code is very efficient because the coefficients drops down quite well exponentially with the number of points. But there is one restriction over here. They must be smooth and differentiable. But our problem, the neutron star, is not the case because we know there is a matter inside, then there is a surface and there is no matter. So there is discontinuity. The density is very high, and then kaboom, there is a surface of the star and there is absolute zero or some artificial atmosphere. So to deal with this problem, of course, we can use the pseudospectrometer like that to solve it, but it will be not efficient anymore. So there's no way, there's no reason to do it. But we can deal with this problem by applying a multi-domain approach. We can construct a surface fitting coordinates, and I think this picture explains a lot. We can divide the region where there's a neutron star and the rest of the space. Of course, there's another star just next to this, and now we have a big picture. There are two stars and there's a numerical grid far away from the center of the system, far away from the binaries. So it is possible to do because this condition about the smoothness of the fields, it tells about the fields within the domain. So we have a lot of domain, and what we need to do is basically we need to deal with the boundary conditions, but this kind of boundary conditions are not physical ones; they're just numerical. We can simply assure that the field itself and its derivative will be smooth and continuous, and that's it. There's no problem over here. So we can apply this pseudospectral method to a different domains separately, and still keep the very high efficiency of the code. So another deal is related to the physical boundary conditions, and I'm not going to talk about it. I just want to underline that there are two different kind of problems. So it is possible to keep the high efficiency of this code by using this kind of coordinates. And let me explain what exactly we are doing with these coordinates. Starting from initial XYZ, it is necessary just to transfer them to the new one, alpha, A, and B. But they are simple, they are invertible, they are free from singularities. It is quite straightforward to do it, and they basically can fit the surface of the star and allows us to go through these calculations efficiently. So these are just coordinate transformations, and I mentioned we are expanding the fields into some basis polynomials. So now let me explain. There are using alpha, A, and B coordinates. There are a set of Chebyshev polynomials together with the collocation points. These collocation points are not equally distant, so we can see it over here. There's a cosine function. So I'm just presenting it for the sake of the clarity that these are the polynomials we are using to do our expansion. So let's move on. So actually, there are very last two slides of this description of the numerical tool. We are dealing with the elliptic equations of second order, and there's a function of this field u, its derivative and its second derivative, and it's supposed to be equal to 0. And this field u, in principle, in our case, is just a conformal factor or alpha or beta or the field of the velocity. But applying this pseudo-spectral method, applying this numerical grid and applying this collocation points allows us to actually trade this differential equation problem for a set of algebraic equations. There's more equations to solve, but there are not differential equations anymore. There are algebraic equations. So, the thing to do is basically to define the u at all fields and all fields to all grid points. So using this, we can write a vector u composed of all of these fields, and additionally we have our original equation, algebraic equation for an enthalpy. So again, there is a solving procedure. We need to solve this elliptic equations because they are not elliptic anymore, they're algebraic, but I'm talking about the equation of the fields, and then ask what kind of enthalpy it generates. And then using this enthalpy, we can iteratively go back to the problem of fields. So there is a very last remark at this point, because we are using the previous state of the system to calculate the new state of the system. We don't have to solve it from the scratch. We don't have to solve it from the very beginning. You can use the previous solution to update and find a new one using basically a Newton-Raphson scheme. So that's the idea here, to save the computational time and to make it even more efficient. Okay, so we are at this point. So it was the very last slide related to the numerical code. And again, I think it's a good moment to ask about the questions.
Someone had a previous question about slides 4 and 5. If you could just quantify nearby, what you mean by nearby. This was back to slides 4 and 5.
I mean,
So
the green part, right?
Yeah, I think it was in the.
Yeah, it was.
Yeah, I think we'll have to we'll have to ask Amnon to re-ask the question, because if we want.
Those questions are available too.
Yeah, my question was that you mentioned that we take 2 TOV stars and place them nearby. Can you quantify nearby? Like, are we simulating the last few cycles? Is that what's happening?
So actually, it was in a first slide. It was 50 kilometers.
So at what stage of the inspiral is that? At what stage of the inspiral do we say they're separated by 50 kilometers? It's close to merger, or is it early inspiral?
So it's, I think, milliseconds from merger, but speaking in terms of the kilometers, the separation is our input. We can set it however we want, and in this case we set it as a 50 kilometers. And let me think, it's maybe 8, maybe 7. The point is, I'm dealing with the eccentric cases, so it's not very easy to just count the number of binary revolutions, but we are talking about 7, 10, 12 binary revolutions before the merger.
Okay.
You will see the
Thank
movie,
you.
by the way, in a couple of minutes.
Oh, okay.
Okay. So it was about S-grid and our numerical tools.
You can close that chat if you want, you think.
Mhm.
We've got about 8 minutes left.
Unfortunately, I cannot change my slide.
No.
Oh, maybe I can. Right. Okay. So as I told, we are dealing with the with the highly eccentric cases. So in this case, we can see the almost two and a little bit of the binary revolutions for one of the star. So so the orbit is clearly very eccentric, and the orbit is so we can see the precession. The other details related to our numerical setup is the type of the equation of state and the value of the masses. We are dealing with the equal masses case and the high spins. So here we have the dimensionless spin parameter equal to almost 0.1. So now let me focus for a while on the spin. So that's the first configuration we are working with, and let's imagine that there is a orbital angular momentum orientated vertically. So in this case, we have the left-hand side orientated diagonally, that's YD, and the right-hand side orientated vertically. So that's the first configuration, diagonal vertical. The second is the diagonal diagonal, diagonal horizontal, and diagonal known. So we would like to basically investigate this kind of spin orientations with the high eccentric case, high eccentric in this case just 0.45. And now there is a movie to look at. And okay, this talk is about the initial data. So actually it's supposed to be enough, because we successfully generated initial data and we incorporated this initial data to Einstein Toolkit. This is a picture of the initial data generated by SGrid, but the picture is a snapshot from the Einstein Toolkit at the t equal to 0. So actually this is enough to justify what we are doing. We were able to load this initial data successfully to Einstein Toolkit, but now let's spend another 41 seconds to look at this movie to look what's going to happen. So the orbit is highly eccentric, and I guess we all know that all of these peaks over here appears when these stars are close to each other. This is the psi4 extracted at r equal to 250. So after a few more binary revolutions, we expect the merger, and then after this merger, we will be able to see the single object for a while, and right now, and eventually, and finally, it's going to collapse into the black hole. Okay, so just one comment at this point. Now we are looking at the remnants. What's here is just the cloud of the gas, but this cloud has a very low density in comparison to the original one. Even if the color palette is the same, because it was adjusted, the order of magnitude is the density. The order of magnitude of this density is the order of magnitude lower than the density we started with for the stars. So there is an empty region inside. Clearly, there is a black hole over there, and some remnants of the matter around. But in principle, it's just almost empty space in comparison to the initial state we started. So yeah, that's the movie, which basically shows the very preliminary results when we started to evolve our initial data. So the very last remark related to what exactly is necessary to do to make SGrid generated initial data possible to load to Einstein Toolkit. For example, we can look at the numerical grid. This is the Einstein Toolkit numerical grid, and on the left-hand side there is our original SGrid. So clearly, it is necessary to read this, to ask Einstein Toolkit what kind of grid was requested by the user, and then it is necessary to interpolate all physical quantities, like all fields, all hydrodynamical variables, to this new grid. And some, of course, there's more details here, but that's the essential part. The Einstein Toolkit must understand what kind of initial data was provided. So remember, I told you I'm going to back to this slide, but now I'm talking about the slide with the title Future Plans. So we would like to make SGRID, our initial data generator, an open book. Up to now, it is just a black box, but we are about to make it public. We would like to public it together with the entire documentation to make everybody just use it. And actually, that's our internal business, because this numerical code is written by a member of the group I'm working. So we can easily do it, but also Einstein Toolkit and Cactus are already open book. I was able to read just a few chapters, so it was very difficult open, and I think at this point it's very good time to thank Leo Wernick and Zagatian for the entire help with reading these two chapters. And of course, this is the explanation what kind of solver and what kind of approach to the hydrodynamic we used in the simulation. But yeah, the Einstein Toolkit, it is an open book, but very hard to read for a very beginning, from the very beginning. So there's one more thing. We have our code written, and we also would like to make it an open book. We would like to incorporate it to the Einstein Toolkit. But in this case, it's not just our internal business. There's a procedure, and we need to follow by some procedures to do the test, to do the consultations. But that's definitely something to do. We would like to make this turn public to let everybody basically use it by incorporating SGRID generated initial data, or basically use SGRID to generate initial data and apply it to Einstein Toolkit. So that's our plan related to our numerical tools. And there is, of course, the plan to make some science. We would like to go through the simulations I just presented with a better resolution. We would like to compare this Einstein Toolkit results with some other codes like for example, BAM or NMesh, which also are able to go through the time-dependent general relativistic hydrodynamic simulations. So all of this stuff is in progress. Partially, we have some results on the black. There is on the left upper plot, there's X, on the then there's Y and Z. I'm talking about the position of the neutron star of the point where the density has a maximum. So we just read initial data over here using a SGRID generated initial data, and we started to evolve them using Einstein Toolkit and the BAM code. So it is very poor resolution, okay? So we are not very worried about the behavior later on, but what we know for sure that we start from the correct data, and we are doing right thing. Additionally, here we have the minimum of the lapse in those two cases. So this is the comparison between Einstein Toolkit and the BAM. And now let me show you also the progress in our research in terms of the better resolution cases. That's the Hamiltonian constraint for one of our runs, this diagonal for a different resolution, 64, 96, 128 numerical grids of the numerical cells across the star. So the general behavior of the Hamiltonian constraint actually is well, we are satisfied. So to summarize this talk, with SGRID, we can generate the initial data for a binary neutron stars with different masses, spins on a different kind of orbit. And actually high spins, high masses, and high mass ratios are available here. We would like to make SGRID and this module for generate this kind of initial data public. And also we would like to make our turn to incorporate SGRID generated initial data to Einstein Toolkit public. So thank you very much.
Where is it? I can't read it. Can you click on the chat? Yeah, okay, so there it is now. All right. All right. Are there any questions for our speaker? Yes.
You spoke about SGRID as an initial data generator. What about loading or Enigma?
Okay. There are. SGRID is just one of the possible choices. Actually, when I started my adventure with Einstein Toolkit, I used Lorraine because then I was working on the S grid just to generate exactly the same thing. So I wanted something with I was interested in something which is already well known and which works. So I started from the Lorraine. It's equally well, but S-grid is better, I think, with generating the cases with Steam.
Carlos?
Yes, I know you're working with neutron stars, but let me bring you back to binary black holes. Because I wanted to refer what you did, how it's related to the two-puncture thorn. And so some coordinate transformation. And if it is a multi-grid version of the two-puncture thorn, something Einstein thought at the time.
So I think in case of the system composed of the neutron star and the black hole, the
Two black holes.
two black holes. So I've never worked with this kind of problem. I had a little bit of experience with the black hole and neutron star. I've never worked with it too.
It's funny. Two black holes are easier.
There
Because so many people ask me, what about one black hole? I don't know what one black hole. I know only to work with two black holes.
well, black holes are easier in terms that there is no internal structure. There is no hydrodynamic inside, right?
Yeah, no, I was wondering how you deal with the punctures and you know, with the pseudospectral method, how you work with something smoother around the punctures. Of course.
So my honest answer is I do not have an experience in this matter.
Can we just?
But it's a completely independent code. You didn't base on two punctures to develop it, right?
So is that possible to set the density to 0?
So density is set to 0, and the
Back here.
but for initial data,
No,
You're not gonna get the singular solution from a code which.
But are we-
To give one.
the question is it possible to try to simulate this kind of initial data, or is it possible to simulate this kind of system by Einstein Toolkit?
Is it trivial to modify that code so that it generates black hole instead of neutron star? They probably no.
I don't know if it's trivial or not, but now I'm thinking about these coordinates which need to fit something. In this case, it needs to fit the surface of the star. What it should be in case of the black hole.
Let's
Horizon?
move on to the next question. We have to wrap up. This will be the last one.
I just want to clarify. So here you solve x and ts. So I mean, you need to move on. You solve x and ts equations in this column. So then you don't have a puncture, you have this excision surface, and you also have neutron star back. Okay, so it's this. But for the any symmetry, symmetries imposed across the current thing, right? We didn't do this for those assessing cases, so there's no restriction in terms of spin magnitude, orientation.
No, I was dealing with the symmetry problem for a while in Einstein Toolkit actually, and there's no symmetry.